And so while we're on the topic, let's very quickly remember what equilibrium constant actually means and how that relates to rate constants. So remember that for this equilibrium of protein binding ligand to form the protein ligand complex, we have an equilibrium. And we can also express what are known as rate constants for this. So again, for this reaction, for ligand is binding to the protein, it's an equilibrium, and we have forward and backwards reverse rate constants. So we call the forward rate constant small k A, and then we call the reverse rate constant small k D. And so this is the forward rate constant. Ka is the forward rate constant, or the association rate constant. And that has units of per molar per second. And that's because on the left-hand side going to the right-hand side, we have we have a bimolecular reaction. So we have both protein and ligand on this side, whereas on the product side we only have one. So the rate constant for this is going to have units of per molar per second, whereas the rate constant for little kd, or the reverse rate constant, or we can also call this dissociation rate constant, has units of per second. Okay? And that's, again, is because on the product side we have two molecules, whereas on the reactant side we only have one. Okay? And so at equilibrium, so remember, equilibrium doesn't mean that nothing is happening either in the forward or the reverse direction. What equilibrium means that the forward and reverse rates now note this is rates, not rate constant, are equal to each other. Mathematically, what that looks like is Ka times P times L. The concentration of P and the concentration of ligand is equal to the dissociation rate constant times the concentration of PL. Okay? So when these two rates are equal, we're at equilibrium. All right? And we can rearrange this into things that are familiar. So for instance, we can rearrange the concentrations on one side. So if we divide the entire formula by the concentration of P and L, what we get is PL over P times. Okay? And what does that look like? That looks like Ka, big Ka, not little Ka. And so if we rearrange that, where we divide by PL, and then we also divide both sides by Kd, what we find is Ka is equal to little ka over little kd. And so that means that the dissociation constant, so big Kd, the association equilibrium constant is going to equal the inverse of that, which is the dissociation rate constant divided by the association rate constant.